my role at ARM is to think about the future of the compute landscape, to make sure that we're providing the right IP for the right markets, and we kind of understand how the compute landscape is changing. I think it's not unreasonable right now to see that in 2 to 3 years, we won't even really be thinking of like classic compute and ML compute, because technologies like large language models will be so integrated with classical compute. So I think, in that future, in a very, very near future, everything we do on our phone or sitting at the laptop, creative work, writing code, creating slides, all of that will be enhanced by large language models. So I think that's pretty clear. But there's a little bit of a wrinkle with that future. So if you take a step back and start looking at the compute demand, what that future entails is just an enormous step function increase in the amount of compute required to enable it. And we want to enable that future. I think it's very exciting. So if you do a little bit of math and say like we've got 4 billion users, each user's doing, let's say, 1,000 inferences per day, like on their phone, on their laptop. And maybe we're using a decent sized model, like 405 billion parameter model. So if you look at that future, do some math, look at existing ML platforms, just to provide the power for that future, you need about 37 nuclear power plants would have to be built. So we don't have time to do that right now, and we want to enable that future quickly. So what's the solution? Well, one is we need lightweight models for the right job. So we just learned about the 1B, 3B models. There's no need for smaller tasks to send the request to the giant brain in the cloud. A lot of things can be serviced by smaller models. And we need to utilize the existing compute infrastructure that we have. We all have phones, we've got laptops, we've got compute in our TVs, in our cars. We need to utilize that infrastructure. It's ready for this. And we need to do just the standard engineering work. We now need to optimize these systems in a way to do the compute more efficiently, to make it run faster, lower latency, just do the standard engineering process. And I think the key that unlocks the flywheel that enables this is actually the open sourcing, which is why it's been so powerful what Meta has done with Llama. Okay, so I'm just going to jump straight into some results. So this is the 3 billion parameter model running on a Redmi K60. This is a Xiaomi phone, which is like a pretty standard phone. It's not a premium phone, very common. And what we've done is we've used a 4-bit quantization method, and I'll talk about later about how we found that method, how we optimized it, and the work we did there. But going from an FP16 version of the model, we're seeing about 20 tokens per second for the prompt processing. We go to 90 tokens per second for prompt. For token generation, you go from a little north of 6 tokens per second up to 18 tokens per second. And that's pretty interesting, because that's kind of the difference between something that's too slow for real time to something that's probably acceptable for real time. Now, this is using quantization, so there's always the question of what's the degradation on the accuracy of your model. And so we have the perplexity plotted there. So you see a pretty minor degradation going from FP16 to the 4-bit quantized model. So pretty great results. This is all done in open source in the llama.cpp framework. That's for these numbers here, but we've since replicated it in ExecuTorch, and people today should be able to go out and generate these results. So how did we actually do this? If you look at the quantization space, it's actually pretty enormous. So there's all sorts of different ways to quantize a model. How big of a vector do you quantize? Do you use linear quantization, or do you use lookup tables, nonlinear quantization? Do you use FP16 scale factors, power of 2 scale factors? It's pretty much an infinite space. So the task for us was to find something that basically is fast, so it can run fast on an ARM CPU, that does not degrade the model accuracy, and is small. So here on this graph, we have the perplexity on the y-axis, and on the x-axis, we have the bits per weight. So the far right there, we have the FP16 model at the baseline. And what you want is something as far to the left as possible and down, right? So you want something that's small, that doesn't actually hurt the perplexity of the model. And what you see here, and this is a testament to the open source community, is working in the llama.cpp framework, we were able to explore all of these different design points. And you can kind of find this, you can see that Pareto curve right there of the orange points, which happen to be nonlinear based quantization. And we would not have been able to do this without open source models. So it really allows us to explore these trade-offs. Now there's an additional caveat to this in that this is talking about the size of the model as well as the impact on perplexity, but these different schemes have very different performance when actually running on a CPU. So what we can also do is then look at the different schemes and see which ones run fast on a CPU. So which ones can I point an expert assembly programmer at and say, hey, roll up your sleeves and make this fast? Or which schemes they say, no way, I can't make this fast on a CPU. So the green points here, which happen to be a 4-bit uniform, non-uniform, and 2-bit uniform, non-uniform schemes, they can actually run very fast on an ARM CPU. And it's kind of interesting, you'll see points that are right next to each other on the curve, but one might be 10x slower when running on a CPU. And we wouldn't have really been able to do this exploration without the open source models. So very exciting. Now, I was talking earlier about how we can't really, we need kind of the right size model for the right job. And what I talked about before for the smaller models also applies to the larger models. So this is a 70 billion parameter model running on Graviton 4, which is an ARM-based CPU system at AWS. This is Llama 3 results, so we are just now getting the 3.2 results for the larger models. But again, we applied that 4-bit quantization. We see a small degradation in complexity, and we see prompt processing of somewhere around 110 tokens per second, and we see token generation with the basically around 70 tokens per second, and that's on a pretty decent size 70 billion parameter model. And this is running on just normal CPUs with highly optimized open source code that's accessible to anyone. Okay, so just pulling it all together, some of the latest numbers. So this is comparing Llama 3.1, the 8 billion parameter model, to the Llama 3.2 3 billion parameter and the Llama 3.2 1 billion parameter. And you see the generation speed with the 4-bit quantization goes from 8.5 tokens per second to 48 tokens per second, which is actually pretty fast. And again, this is just running on a commodity CPU they're just sitting around everywhere. And the model size, similarly decreasing that parameter count and using the 4-bit quantization, we're going from 4 gigabyte model at the top to roughly 0.5 gigabyte at the bottom. So you're also really decreasing your footprint and your required memory requirements. So I think in summary, the large language LLM inference, it's going to happen everywhere. There's a lot of ML to go around, so some stuff will still run on big, huge systems, but smaller models will run everywhere. And the open sourcing is the key to unlock the innovation. We couldn't have done all these optimizations if we didn't have those open source models. We've taken these optimizations that we've done in software and we've wrapped them in a program called Kleidi AI, which we're using to integrate now into different open source frameworks to improve the performance of machine learning workloads on ARM CPUs. And like I said before, we've integrated that into Executorch. So I have a little demo here of the 1 billion parameter model, just doing a chat bot. And again, this is running on a standard CPU, and you can just see the token generation here is just pretty blazingly fast. And I would not have thought a couple years ago we'd be able to do that. So there you go, you see it, it's very fast. Cool, and that's it. So thank you very much.